Okay, so for this Chapter 3 introduction, we're going to talk about equilibrium analysis in extended body systems. This is different than concurrent force systems. So what we're going to do in this, we're going to take what we were doing with concurrent force systems and we're going to add in a new part. So we still sum up all the forces, make them equal to 0, just like we did before, but now we have to worry about moments. We have to worry about moments because we are no longer in a concurrent force system. Some of those forces are going to cause moments. And so moments until now, we've just been kind of talking about them as one simple thing, but really moments are pretty complex. And so we're going to break down moments into a number of different topics, a number of different ways to deal with them. And so with moments, the big decision you need to make is whether or not you're going to calculate moments using scalar calculations. And so these are just regular equations, no vectors, or we can use vector operations, specifically the cross product, to calculate the moments from a force as well. And so both of these are moments about a particular point. It can be the moment about any point, and the sum of moments about any point must be equal to 0 if that body is in equilibrium. All right, so generally our scalar calculations are going to be better for 2D systems, while our vector calculations are going to be better for 3D systems. It's just the easier way to deal with it in either of the two setups. All right, so also with scalar calculations, we also are going to use something called Varignon's theorem. So just like we could break down forces into x and y components earlier on, we're going to take those same forces, we're going to break them down in x and y components again, and by breaking them down in x and y components, it actually makes calculating the sum of a bunch of moments a lot easier. So generally we're going to use Varignon's theorem, we're going to break down those forces, find the moments individually of each of the components. So with vector calculations, something else we can do here that we will need to do sometimes is we can find the moment. If we've got some moment about a point, we can also find some moment about a particular axis. So this is pretty easy if it's just simply the moment about the x-axis or the y-axis. We just pull out the component of that moment from our moment about a point calculation. But say we've got something like a hinge or a shaft or something that doesn't quite line up, we can use something that's called the dot product, which is a vector operation similar to the cross product, to find the moment about that particular axis. So the last thing we're going to talk about with moments is we also sometimes talk about couples. And so a couple is a set of equal and opposite forces that is not collinear. And so they don't quite line up with one another. And because they don't line up with one another, they're going to cause rotation. But since the forces are equal and opposite, they don't cause any linear acceleration. So a couple is sometimes called a pure moment because it would cause rotation without causing any sort of linear acceleration. So we've got all these different options for analyzing moments. Depending on the problem, depending on how our equilibrium analysis goes, we might want to use one method over the other, but all of these options are going to go into equilibrium analysis for an extended body. So just like we had the sum of forces before, we're going to continue that process, and we're just adding in this new element to the analysis. We're going to add in the fact that the sum of the moments must also be equal to 0 if the body's in equilibrium. And so we know if there's no angular acceleration, sum of the moments must be equal to 0. All right, so that is our introduction for Chapter 3. Thank you for watching.